In this lesson, we're going to have a brief review of the unit circle to make sure we understand how all the pieces fit together so that we can use it to help us evaluate certain trig values. So we'll start off with this picture that many of you have probably seen. As you can see, I've put yikes here because it looks really scary, especially when you realize you need to know all of these values and won't have a graph like this to refer to on the AP exam or on any of your exams in this class. So what we want to do is bring this whole thing down to scale, but also make sure you understand why it works. So the why it works is what we're going to be doing in this video, and then there'll be a second one that shows you how to use it in specific problems. All right, so let's just start with some of the basics of the unit circle, and we should start off with talking about why do we call it a unit circle. It's called a unit circle because the radius equals 1. And since the radius equals 1, we also know the circumference, because circumference is 2 pi r, so 2 pi times 1 equals 2 pi. So we know the circumference of this circle, and we know the radius, and we're going to draw in the radius here. So that's 1. And with this radius, we can draw a triangle like this, a right triangle, and we'll see that we go over x units this way, and that'll give us our x coordinate. And then we move up y units, and that gives us our y coordinate. Furthermore, we'll put an angle theta here, and it turns out that we can do the sine of theta. We know sine is opposite over hypotenuse, so y is on the opposite side, 1 is on the hypotenuse, y over 1, and we see that the sine of theta equals 1, which means that instead of writing y here, we could write sine of theta. Cosine of theta, we know, is adjacent over hypotenuse. Here's our adjacent side x. Our hypotenuse is 1 again. X over 1 equals x. That means that the x coordinate is the same thing as the cosine of theta. And then finally, tangent of theta is opposite over adjacent. Y is our opposite side. X is our adjacent. So we have y over x. And we all know that y from up above is the sine of theta. X is the cosine of theta, and we get a relationship that we studied in pre-calculus as well, that the tangent of theta equals sine theta over cosine theta. All right, so let's start by labeling our axes. We already talked about how the circumference is 2 pi. So if we start at 0 here and go all the way around one time, we've traveled a distance of 2 pi units. So if we go halfway, we're at pi. If we go halfway to pi, well, that's pi over 2, half of pi. And if we go all the way down here, it's 1.5 pi, which we usually like to write 3 halves of pi, because we're counting how many halves we have. We have 1 half, 2 halves. Here we're 3 halves. And up here we're at 4 halves, and 4 halves is 2. We can also label the coordinates of each of these. So right here we're at 1, 0, because the radius is 1. Up here, 0, 1. Over here, -1, 0. And down here we're at 0, -1. And this allows us to do things like this. If I asked you for the sine of pi over 2, we would come over here and say, well, the sine is the y coordinate, which is 1. So I've got 1. If I asked for the cosine of pi, I would go over here to pi. Cosine is the x coordinate. It's -1. If I asked for the tangent of 3 pi over 2, I would go down here to 3 pi over 2, and I'd take y over x, -1 over 0, and I'd say, well, I can't divide by 0, so that answer is going to be undefined. Okay. So now, what happens if we cut our pi into fourths? So we know we're at 0 here, and we're at pi here, and so we've divided this into fourths. So here's 1/4 of pi, which is pi over 4. Here we're at 2/4, and 2/4 reduces to pi over 2. Here's 3/4 of pi. 4/4 is a full pi. 5/4. 6/4 of pi, which reduces to 3 pi over 2. 7/4 of pi. And then finally, we're back up here with 8/4 of pi, which reduces to 2 pi. Now, a nice thing to see is that every single fraction that is over 4 is on the square, right, like this. So anytime you're asked to evaluate anything that's over 4, it's going to be across from pi over 4. All right, so now let's divide our pi into 6. So when we divide our pi into 6, we're going to start here as 0. Here is the distance to pi, and so here we go. 1/6 of the way to pi is pi over 6. 2/6, well, that's just 1/3, or pi over 3. Here we have had 3/6, so that's pi over 2. Here's 4/6, which reduces to 2 pi over 3. 5/6, 5 pi over 6. 6/6, which is a full pi. 7/6, 8/6, which reduces to 4 pi over 3. 9/6, which would reduce to 3 pi over 2. 10/6, 5 pi over 3. 11/6 of pi. And lastly, we're back here, 12/6 of pi, which reduces to 2 pi. And then we'll notice here that everything that was over 6 is in this red rectangle. This is going to help us later on, because if I know the coordinates for pi over 6, I can reflect to get the coordinates for 5 pi over 6, 7 pi over 6, or 11 pi over 6. In the same way, if I know the coordinates for pi over 3, I simply reflect for 2 pi over 3, 4 pi over 3, or 5 pi over 3. So everything that's over 3 makes a rectangle, and everything that's over 6 makes a rectangle. All right, so now we need to review back to our geometry, our knowledge of some special right triangles. So we're going to start here, and we're going to have pi over 4 as our central angle, and we'll recall that that's the same thing as 45 degrees. So I've drawn it larger out here, 45, 45, 90 triangle. Since it's isosceles, we like to call each of these sides 1, and just using Pythagorean theorem, 1 squared plus 1 squared, that gives us 2. Square root of 2 is going to be our hypotenuse using the Pythagorean theorem. And this is the ratio that you would have learned back in geometry, that any 45, 45, 90 triangle has the ratio of 1 to 1 to root 2. The only problem is on the hypotenuse here, I want that length to be 1. So to get a similar triangle, I divide all of the sides by root 2. So I've done that. Only problem is I also need to rationalize these. So here we go, root 2 over 2 and root 2 over 2. And now I can put these values on here, root 2 over 2 and root 2 over 2, which means the coordinates right here are root 2 over 2, root 2 over 2. I also want to point out that root 2 over 2, and this is just a helpful fact to remember, is about 0.707. And so if you think about this, we know that this is 1 right here, and you'll notice that this being right around 0.7, that makes sense. Just even on a roughly drawn one, 0.5 is about here, and this is being 0.7 makes sense. Same thing up here, 0.5 is about here. Here's our 0.707. This is useful if I want to find something like, say, the sine of pi over 4. And I'd say, oh, that's the x or the y coordinate. So that's root 2 over 2. Or perhaps I want the cosine of 3 pi over 4. I would go here and say, well, there's 1 pi, 2 pi. Here's 3 pi. I would reflect it. Cosine is the x-coordinate. When I reflect it, it becomes negative root 2 over 2 because my x-coordinate becomes negative over here. I can just reflect it to find that other value. All right, let's move on to our next special triangle. In this one, we're going to be working with pi over 6, which is the same as 30 degrees. So if you recall from geometry, you memorized your 30, 60, 90 triangles. When you would have done this in geometry, it's convenient to make that side length 1. You actually place another 30, 60, 90 down here. And when you do that, you get an equilateral triangle. With this line of symmetry right here, that's 1, this is 1, this whole length is 2, it's equilateral, so this is 2. Pythagorean theorem, 1 squared plus b squared equals 2 squared, and we're going to get that b is the square root of 3. So here's this side, root 3. Only problem is on our unit circle, the hypotenuse has to be 1. So we're going to divide all of these by 2 to get that similar triangle. So we've done that, and we get our sides as being root 3 over 2 and 1/2, which means right here we get the coordinates of root 3 over 2, there's our x, and 1/2. So our side note here is that root 3 over 2 is approximately 0.866. And of course, 1/2 is 1/2. And you're going to be able to see that if you look at this, this is the distance out here is to 1. And right here, we'll see, I mean, that rounds to almost 0.9. You can see how close it is to 1. Whereas if we go up on the y-axis, if this is 1, halfway is right there. And look at that. There's our point. It's halfway up. All right, so if we were to use this, we might do something like the cosine of pi over 6, and we'd say, well, cosine is the x-coordinate, and so it is root 3 over 2. Now, similarly, if I have this angle, pi over 3, well, that's really the same triangle we just looked at, because if we draw it over here, that's 60 here, and this is 30, and that's the exact same measures. Recall this was 1, 1/2, and root 3 over 2. So now we've got the same idea, but we just switched our x and y. This is 1/2 and root 3 over 2. Now the way I always remember this is I look to see which one is 1/2. I look across, I'm like, oh look, I went halfway across. That's the one that's 1/2. I look here at my y value and I'm like, well, that's almost all the way to 1, so that's got to be the one that's the 0.866 or the root 3 over 2. So let's just try one like this. What if I asked you for the sine of negative pi over 3? Well, if you're going to negative pi over 3, you'd come down here, and you know you'd be reflecting over the x-axis, which means that the y-coordinate changes. So that'd be 1/2 negative root 3 over 2, and I've got my answer. It's the y-coordinate. It's negative root 3 over 2. All right, so we've learned all the basics we need, and now we just got to talk about what is it that we need to memorize. Now, I'm going to pull out that scary picture again. Remember, we started with this in the beginning, and there it is. And that looks really frightening to memorize. We need to know all of that, but to know that, let me just get it down to size. What do I really need to remember? And what I really need to know in order to solve these problems is that a unit circle has a radius of 1. So this is at 1, 0, and this is at 0, 1, and anything else I can reflect. I need to straight memorize that this is root 2 over 2, root 2 over 2. For the other two, I know one is 1/2 and the other is root 3 over 2. I look to see which one's, oh, this one is not halfway over, it's most of the way over, so it's root 3 over 2, and it's halfway up, so that's 1/2. And then this is 1/2 root 3 over 2. I've got memorized that this is pi, so I can divide it into any fraction. And finally, I know that the sine is the y-coordinate, cosine is the x-coordinate, and tangent is y over x. And if I've got those things memorized, I can figure out any problem I need to do. All right, you can watch the next video to actually watch me do some problems.